Okay. All right, let me share a screen. So you should be, I don't have my other iPad set up. So you should be seeing my whiteboard screen, yeah?
Yeah.
Okay. So we're going to look at series circuits and parallel circuits. So we know, let's go through the basic guidelines first and see how they compare. Okay, so let's look at a comparison of series circuits and parallel circuits. In a series circuit, the current is the same in all resistors. In a parallel circuit, oops, current is different in each resistor. And we have to put the caveat unless all resistors are the same. In a series circuit, there's only one current path. There's only one way the current can go. In a parallel circuit, there are multiple current paths. In a series circuit, the voltage across the resistors are different. And again, we have the caveat unless all resistors are the same. In a parallel circuit, the voltage across the resistors is the same. In a series circuit, REQ has to be greater than the equivalent resistance has to be greater than the largest resistor value. In a parallel circuit, the REQ has to be less than the smallest resistor. So we know it's got to be less than the smallest. We also had the rule with the parallel that the R max is going to be R smallest over N, where N is the number of resistors. Okay. In a series circuit, resistors share one node. So in other words, if we did the list of nodes with R1 connects between A and B and go on from there and whatever, we'd see that only one letter is the same for resistors in series. In parallel, resistors share two nodes. Let me see if there's anything else we usually talk about. I think that's pretty much the key ideas. So the big things to remember is that in a series circuit, the current's the same, but in a parallel circuit, the voltage is the same, right? So series, the current stays the same. Parallel, the voltage stays the same. All right. In a parallel, the currents are different. And in a series, the voltages are different unless the resistances are all the same. Okay.
Mhm.
You good on that? Questions on any of that?
No.
Okay. So let's do a quick calculation. So if we had, let's say we had that, and this was node A, this was node B, this was node C, and this was our reference node or ground. I'll just call it, well, we'll just put the ground symbol in. So if we wanted to do this, the general approach to a series circuit like this is you find RT, you find IT, and then you use IT to find the voltages. And you could also use voltage division to find the voltages. So if we did that in this case, we would say that RT series circuit, oh, that's what I knew I wanted to put over there. Let me go back to the other page and add that to the bottom. So it's all on one page. Um, the REQ for a series circuit is going to be R1 plus R2 plus R3, and we just keep adding for as many as we've got. And for a parallel circuit, the REQ is 1 over R1 plus 1 over R2 plus 1 over R3. And you do that for as many as you've got, and then you take the reciprocal of that whole thing. Okay? So we have to remember the formula for series. We remember that one of the key things always to remember is that you've always got Ohm's law, V equals I times R, or I equals V over R, or R equals V over I, depending on what you want to do. That always works. In a series circuit, you had, what color am I up to? Kirchhoff's voltage law, which said Vs is equal to VR1 plus VR2 plus VR3 for as many voltage across resistors as you've got. And in a parallel circuit, you have Kirchhoff's current law, which says that IT is equal to IR1 plus IR2 plus IR3 for as many as you've got in parallel. Okay, so you got Kirchhoff's voltage law for the series circuits, Kirchhoff's current law for the parallel circuits. All right. So RT is going to be R1 plus R2. This is a close REQ. Oops. It's the sum of the resistors. I've got 3, so I've got 330 plus 270 plus 100. So that gives me a total resistance of 700 ohms. I could find IT. Let me go back and do that. Do this first. One of the things I would recommend, and we'll see it more when we get to series parallel, because we're going to do a lot of calculations like that, is you redraw this to show the equivalent resistance. This is my REQ. So in this case, it turned out to be 700 ohms. All right. So now, and this came up on the quiz, if I look at this, I don't know the voltage across R1. I don't know the voltage across R2. I don't know the voltage across R3. I know that the 3 voltages add up to be 14, but I don't know what any one of the individuals are. Once I calculate my REQ, I have 1 resistance and 1 voltage. So I could just easily write, I'm going to write it a little bit lower so I get a little more room later on. IT is Vs over REQ. So I've got 14 volts divided by 700 ohms. What is that, 20 milliamps? Let me just double check that. Yeah, 1K would be.
It's 20 milliamps.
Okay, thank you.
No problem.
So now we know that in this circuit, IT is 20 milliamps. That also means that we have in this circuit $20 milliamps. So now I know the current through R1, the current through R2, the current through R3. So now what I could do is I can solve VAB is going to be between A and B is R1. So it's going to be IT times R1. So I have 20 milliamps times 330 should be 6.6 volts. VBC, between B and C, we have R2, so it's IT times R2, 20 milliamps times 270, 5.4 volts. And just to be different, let's find VC to ground using voltage divider. Using the voltage divider theorem, it says that it's the one you want to find the voltage across, which in this case is R3, because from C to ground, we've got R3, divided by REQ times V sub S. So I've got 100 over 700 times 14 volts should be 2 volts. And we can do a quick check. KVL says VS should be equal to VR1 plus VR2 plus VR3. I'll just do it right over here. I've got 6 for VR1, 6 for, or we actually could have written this as VAB plus VBC plus VC to ground. I've got 6.6 plus 5.4 is 12. 12 plus 2 is 14. So it does indeed check. Okay. I could also find in a series circuit, I could do something like calculate VB. Well, VB, since there's no second subscript, is to ground. So VB would be VR2 plus VR3. So we could say that VB is going to be VBC plus V sub C. So VBC, we figured out to be 5.4 volts. VC, we figured out to be 2 volts. That makes VB 7.4 volts. And I could also have gone the other way. I could have really said VBA plus VA. If you remember, if I put this in, this was 6.6 volts. Current goes into the positive end, so it's going into the left end, making that positive. It leaves on the other end, the right end, which is the negative end. So now VBA, I hit the negative sign first. So this would have been negative 6.6 volts. From A to ground, this is the positive end of the battery, so we hit the A first. So this becomes plus 14 volts. When I do the math here, this works out to be
7.4.
7.4 volts. So regardless of whether I go clockwise or I go counterclockwise, you come up with the same answer. You just have to remember to put the voltages in so you know which polarity to use. If I
Yeah.
did VBC, this would have been 5.4 volts plus at the top, minus at the bottom. This would have been 2 volts plus on the right, minus on the left. So it would have been plus 5.4 plus 2, which is what we got when we did it over here. Any questions on any of that?
No.
No.
We good?
Yeah.
Yeah.
Okay. So let's take a look at a parallel circuit. So we did voltage division, we did calculations. Yeah, okay. So let's look at a parallel circuit. Let me just do a quick calculation. All right, so before we even start, the range, let's figure out the range for the REQ. So REQ has to be less than the smallest. So it's got to be less than 300. And REQ has to be greater than the smallest 300 divided by 3. So that's 100. Did I write that right over here? No. This should be min. Not max. This should be min. Has to be greater than this, but less than that. As I was writing, it did make sense. All right, so we know when we do our REQ calculation, we should end up with something between 100 and 300. So REQ, again, we're going to calculate REQ, we'll calculate IT, and then we'll calculate the individual I sub R's if that's what's requested. And we'll do one by current division. So REQ is 1 over R1 plus 1 over R2 plus 1 over R3. Take the reciprocal of that. So I have 1 over 1.5K plus 1 over 1K plus.
I'm sorry, it's 9 volts, right? For the
9 volts. Yep.
Okay, thank.
Yep. 1 divided by 300. So that should come out to be 200 ohms. Somebody want to double check that?
Yeah, that's right.
Okay. I could solve for IR1, IR2, IR3 right now. I could turn around and just say that IR1 is VS over R1. So I've got 9 volts divided by 1.5 K. So that should be 6 milliamps. IR2 is going to be VS over R2, 9 volts divided by 1K, which is 9 milliamps. And just to do current division, let's solve for the IR3 that way. IR3, remember with current division, we said that oh, I didn't do voltage division, current division over here. Okay. Current division, we take the REQ and put it on the top and put the one we want to find the current through on the bottom. So it's the inverse of voltage division. And we multiply that times IT. Well, we need to find IT first. IT is going to be VS. Actually, we should do the same thing we did. Oh, by the way, we didn't check. Our 200 ohms does indeed fall between the 100 and 300, which we said was our range. So the IT is VS over REQ. That always works. So we have 9 volts divided by 200 ohms should be
45 milliamps.
45 milliamps.
Yeah. Yeah.
Okay. So now we know the IT, so we can say IT is going to be, REQ is going to be 200 divided by R3, which is 300, times 45 milliamps. So that should come out to be 30 milliamps for I sub R3. 2/3 of 45 is 30. And as my check, we can say that IT should be IR1 plus IR2 plus IR3. So IT is 45 milliamps. And that should be 6 milliamps plus 9 milliamps plus 30 milliamps Six plus 9 is 15 plus 30 is 45. So it does indeed check out. Questions? Or are we good?
I think we're good.
Yeah, we get.
Okay. That's pretty much it. As long as you,
Can you go over the some of the multiple choices that you're gonna put, like some model? I mean, it's up to you.
well, I mean,
So, sir,
remember,
are you gonna put the power stuff?
yeah, there will be. Oh, yeah, thank you for reminding me. So let's do some calculations of power. Let's say calculate P sub R3. So if we wanted to calculate P sub R3, we know the power formula, there's three forms: V squared over R, I squared R, I times V. Probably the one that I would use here would be V squared over R, because the voltage is given and the resistance is given. Even though we checked it, if I had gotten these backwards somehow and I used, or I calculated this wrong, if you use I squared R or I times V, if you calculate I wrong, you've got definitely wrong power. So I would definitely use this. So this would be what? 9 volts squared divided by 300. So 81 divided by 300 is 270 milliwatts.
Yeah.
Okay, so that could be a power problem. If we wanted to do P total, the total power, you could solve as either P R1 plus P R, wow. Did the same thing. Write the plus and I will automatically want to write R. Plus P sub R2 plus P sub R3. Or that would require me to calculate the power for R1 and the power for R2. Or I could calculate P total is V sub S squared over REQ. Or I could calculate P total is V sub S times IT. Either of the last two, you're involving a calculation. In this one, you'd be calculating REQ, using a calculated value of REQ. And in this one, you use a calculated value of IT. So either way, you're using one given and one calculated. Here, you're practically using 3 calculated values. So I would stay away from this one. And probably it's easier to multiply than, this is a square and then a division. This is just a straight up multiplication. So let's just do it with straight up multiplication. So VS times 45 milliamps, was it? Yeah. So P total is 36 plus 40.5. Let me see. 450. 9 times 405. Decimal points in the wrong spot. 405 milliwatts. If I go back to the series one and calculate some powers, let's say I wanted to calculate P sub R2. Now I have no choice. If I use V squared over R, I'm using a calculated power. If I use I squared R, I'm using a calculated IT value. So it really doesn't matter. I would probably use one I squared R or V squared over R. V squared over R involves 2 steps of calculations. So I'll probably just stick with IT squared times R 2. So my IT for this one was 20 milliamps times R2, which is 270. So that's 108 milliwatts. And if I wanted to calculate P total, it's just going to be IT times VS, the easiest way. So 20 milliamps times 14 volts. $280 milliwatts. Okay. We good? Questions?
No.
Professor, for PR2,
Yeah.
for that one, like, how'd you
Oh.
put in the calculator?
Oh, you know, yeah, because wait, hold on. Yeah, let me do this first. So if I was going to put this in the calculator, what I would put in is 20 EE, second EE, minus sign, not the minus sign, but the one in the brackets, change sign.
Yeah.
The key, that's a key, 3, and then the X squared key times where was I? 270. And enter. I'm really right at the edge of my tablet here. It's awkward to write. So it's 20 second function EE change sign 3. So that's 20 milli X squared times 270 and hit enter. When you do this, the calculator is sitting there going, I got an exponent and I got a multiplication that you just told me to do. PEMDAS says do this one first. So it's going to square this, then it's going to multiply by the 270. So it'll make it work. Did you get it, Carlos?
Yeah, I got it.
Okay.
And will we have to like find the value of a resistor?
I don't think so. I'm probably just going to do a straight up parallel and a straight up series.
Okay. And like, what chapters should we read to do the multiple choice?
Chapter 4 was power. So if you don't remember the power stuff, the formulas, that's chapter 4. 5 is series circuits and 6 is parallel circuits.
Okay.
So I would, look through 4, 5, and well, I'm not going to ask any conceptual questions on power. I'll just ask questions, conceptual questions on series and parallel. And somebody asked about those before, and the conceptual stuff would be the stuff that we had here. You know,
Okay.
so, you know, if you understand this stuff, that's really the conceptual stuff. You know, there's no calculations in this stuff. It's just, you know that in a series circuit, the current's the same. In a parallel circuit, the voltage is the same. You know, there's only one current path. There's multiple current paths in the parallel. You know, that conceptual stuff is the stuff I'd ask on multiple choice or fill in the blank.
How many questions will be there for the quiz
Say
on
that again.
Thursday? How many questions will be there for the test?
I don't know. I haven't made it up yet.
No
So
problem.
usually what I'll do is I'll tell Professor Atwood how long it took me to do it. And then, like I said, I double it or triple it. Whatever time it takes me, I double or triple and figure that's, you know, the average time for, you know, somebody that's doing it as an exam to do. So you got plenty of time. So I'll let him know how long it took me and how long I recommend giving him. And obviously, you know, if he's proctoring an exam, there are still people that are struggling. But I'm always amazed at, and I really saw this when I taught physics, is, you know, I'll watch somebody and they'll finish the exam and then they'll check their answers 4 different ways to come up with the same answer for the 4th time and still want to check it again and go, you know, I think it was, is it Edison? Somebody said, crazy is doing the same thing over and over and over again and expecting a different result. You know, at some point you say, okay, I did the problem, I checked it, I came up with the same answer when I checked it that I did when I did the problem, so I'm done. So, but, okay. Any other questions?
No, I think that's it.
Okay, then
I
I'm
think
gonna
that's
wrap
it.
it up.
Yeah.
I'm gonna wrap it up and I'll put the video for anybody that couldn't make it, and I'll send out an email with the link.
Are you planning to put another review section, or this is your like
I think
tomorrow?
this is pretty much it because I know I've got a lab session with my ELT112 class tomorrow. So it's probably, I think if they watch, anybody that watched the video, and I'll put in my email that if you have specific questions and you didn't, you know, some questions about something that I went over on this session, feel free to email me. So,
Sure.
all righty.
Yep.
All right, take care, Professor.
All right, gentlemen.
Thank you
Take
so much,
care.
Professor.
All right, take care.
Thank you. Thank you, Professor.
Okay, take care. I gotta stop sharing before I can end.